anywhere in space, but that's not too meaningful. So you take them into your circuits. And so you define the loop first. Then you define the direction in which you want to march around that circuit. You attach an open surface to that closed loop. And you can determine on that entire surface the integral of B dot dA. Everywhere on that surface, locally you know the dA, locally you know the B, you do the integration and you get your magnetic flux. And then if you know the time change of that magnetic flux, then you know the EMF. If you go around in this conducting circuit and you measure everywhere the electric field, then the integral of E dot dL, if you go around the loop, will give you the same answer. And that connects the two. The magnetic flux change is connected with the integral of E dot dL when you go around. You have to take that minus sign into account. How come it doesn't matter whether you choose a flat surface or whether you choose a bag? Well, think of magnetic field lines as a flow of water or spaghetti, if you like that, or a flow of air. It is clear that if there is some kind of a flow of air through this opening, then it's got to come out somewhere. So it always comes out of this surface. And therefore, you're really free to choose that surface. So you always pick a surface that is the best one for you. Now all this looks very complicated. But in practice it really isn't. Because your loop is always a conducting wire in your circuit. And the minus sign is never an issue because you always know with Lenz's law in which direction the EMF is. In fact, when I solve these problems, I don't even look at the minus sign. I ignore it completely. I calculate the magnetic flux change, and then I always know in which direction the current is. So I don't even look at the minus sign. Now I want to show you a demonstration which is very much like what Faraday tried to do. I have here a solenoid. We've seen this one before. We can generate quite a strong magnetic field with that. And we're going to put around this solenoid one loop, like we had here, like Faraday did. And then we're going to close the switch. And so we're going to build up this magnetic field, and we're going to see the current in that loop. And so if we make a cross-section straight through here, then it will look as follows. Then you see here the solenoid. So the magnetic field is really confined to the solenoid. Magnetic field outside the solenoid, as we discussed earlier, is almost zero. So there's only a magnetic field right here. Keep that in mind in what follows. And now we're going to put a wire around it with an ammeter in there. If the magnetic field comes out of the board and is growing, is increasing, the current will flow in this direction. Lenz's law. If it is decreasing, the current will go in the opposite direction. Now keep in mind that the magnetic flux through this surface, that is my surface which I attach to this closed loop, that magnetic flux remains the same whether I make the loop this big or whether I make the loop very crooked, like so, because the magnetic flux is only confined to the inner portion of the solenoid, and that's not changing. And so when I change the shape of this outer loop, you will not see any change in the current. I hope that doesn't confuse you. I'm going to purposely change the size of the loop. And so I'm going to do that now. You're going to see there a very sensitive ammeter. And you're going to see here this loop, the big wire, and I'm going to just put it over this solenoid. Let me first make sure that my ammeter, which is extremely sensitive, I can zero it. It's sign sensitive. If the current goes in one direction, you will see the needle go in one direction. If the current goes in the other direction, you will see the change. And so now I put this loop around here. Crazy shape, this loop. So it's around this solenoid once. So the magnetic field is inside the solenoid. And so think of a surface which is attached to this crazy loop. And now I'm going to turn the current on, and only while the current is changing will there be a changing magnetic flux. Only during that portion will you see a current flow. 3, 2, 1, 0. I will break the current. 3, 2, 1, 0. Went the other direction. If I change the size of the loop, I'm making it now different. Much smaller makes no difference for reasons that I explained to you, because the magnetic flux is not determined in this case by the size of my loop, but is determined by the solenoid. So if I do it again now, with a very different shape of the loop, let me zero this again. 3, 2, 1, 0. 3, 2, 1, 0. No change. Almost the same what you saw before. Now comes something that may not be so intuitive to you. I'm now going to wrap this wire 3 times around. And so this outer loop, this outer conducting wire, is now like this. 1, 2, 3. Something like that. Now I have to attach in my head a surface to this closed loop. My God, what does it look like? What a ridiculous surface. Well, that's your problem, not Faraday's problem. How can you imagine that there is a surface attached to this loop? Well, take the whole thing and dip it in soap. Take it out and see what you see. The soap will attach everywhere on the conducting loop. And if this loop were like this, going up like a spiral staircase, you're going to get a surface that goes up like this. But the magnetic fields go through all 3 of them. Therefore, the changing magnetic flux will go 3 times through the surface now. And so Faraday says, fine, then you're going to see 3 times the EMF that you would see if there were only one loop. And if you go 1,000 times around, you get 1,000 times the EMF of one loop. Not so intuitive. So, I'm around now once, I go around twice, and I go around the 3rd time. I have 3 loops around it now. I can zero that, but that's not so important. 3, 2, 1, 0. You saw a much larger current. It's about 3 times larger because the EMF is